In this video, we are going to begin to study how we can determine when a series converges or when it diverges. And we start by examining series with positive terms. This is also known as a positive series. All right, so a positive series is a series in which each term is positive. That makes sense. Right? So a sub n is greater than 0 for all values of n. Right, so what we can do is we can, quote unquote, visualize the terms of a positive series as rectangles, right, with width 1 and height a sub n. As such. So it has a width of 1 and a height, let's say, of a sub n, right? So that's the nth. I'll just use the lowercase n. Right. Well, then this sum, let's say it goes from 1 to capital N, is just the sum of the areas, right, of the n rectangles. So the key feature of positive series is that their partial sums form a monotonic increasing sequence. All right, well, since it's a monotonic increasing sequence, there are only two possibilities. It's either bounded or unbounded, right? So that comes from our study of sequences, and that is given here. If a sub n is a positive series, then either 1, the partial sums are bounded above, in which case the series converges. Or, number 2, the partial sums are not bounded above. In which case the series diverges. These are the only two possibilities for positive series. Now, notice that this remains true. If a sub n is greater than or equal to 0 for all n, and if a sub n is greater than 0 for all n greater than or equal to capital M. Right, for some value m, right? If we look at the first one, that makes sense. Right, if you add 0, it's not going to change the next sum, right? So adding 0 doesn't change anything. Since we care about what the sequence does in the long run, right? As long as it's positive after some point m, then that's how the series is going to behave, right? As long as for some finite values before, that can do whatever it wants, it's still going to converge in the long run. Right? Or it's still going to be a positive series in the long run if all the terms are positive after some point. So let's suppose a sub n is equal to f of n, where f is a positive decreasing function. Oh, decreasing and continuous, sorry. And continuous function. Of x for all x greater than or equal to 1. Using the right endpoint approximation, for area, what we're going to get is rectangles that lie below the curve. Right? That can be seen here. Right, so remember, with right endpoint, what we do is we take the height of each rectangle to be the right endpoint of each subinterval. Right? So these would be our rectangles. This area represents a sub 1, right? This would be a sub 2, a sub 3, so on and so forth. And this one here would be a sub n. Right, so for all n, notice what we have. A2 plus A3 plus A4 plus so on and so forth plus A sub n would be less than or equal to the integral from 1 to n of f of x dx, which would clearly be less than or equal to the integral from 1 to infinity of f of x dx. If this integral converges, then this sum right here is bounded above, right, by a finite value. Notice that what that means is that the sequence of partial sums is bounded above. That would mean that this series converges. On the other hand, if we use the left endpoint approximation, for area, the rectangles all lie above the curve of f. So let's try and mimic the curve from above. Close enough. But remember, with left endpoint, you take the left endpoint of each subinterval to be the height of the rectangle. All right, so these would then become our rectangles. Right, this rectangle would represent A1, A2, A3, so on and so forth until we get to AN. Oh, I'm sorry, AN minus 1, let's call it. Now notice in this case, what we have is the integral from 1 to n of f of x dx would be less than or equal to this sum. If this integral diverges then this integral will approach infinity as n does. What this means is that the sequence of sums also tends to infinity. Right, so the partial sums also tend to infinity, which implies that the series diverges. So we now formally state this as our second test. It's the integral test. So we let a sub n equal f of n, where f is positive, decreasing, and continuous for all x greater than or equal to 1. If the integral from 1 to infinity of f of x converges, then the series n equals 1 to infinity of a sub n converges. If the integral from 1 to infinity of f of x diverges, then the series n equals 1 to infinity of a sub n diverges. We're going to examine this series for convergence. It should be 1 over n cubed. So what we do is we say, let f of x be 1 over x cubed. Well, clearly, f is positive for all x greater than or equal to 1. It is clearly decreasing for all x greater than or equal to 1. And it is also clearly continuous for all x greater than or equal to 1. Now take a look at the integral from 1 to infinity of dx over x cubed. Well, this converges, right? Because this is a p integral. With p equal to 3. Right, which converges. We don't care what it's converging to. All we care about is that it does converge. So what we can conclude is that this series converges by the integral test. We're now going to examine this series. For convergence. So we say let f of x be 1 over the square root of 2x minus 1. This is clearly positive. Clearly decreasing. And clearly continuous, again, for all x greater than or equal to 1. Now let's take a look at the integral from 1 to infinity of 1 over the square root of 2x minus 1 dx. Right, so recall that this would be the limit as b approaches infinity of the integral from 1 to b. And let's write it this way. All right, so that antiderivative would just be 2x minus 1 to the 1/2 power. That gets evaluated. X goes 1 to b. We get 2b minus 1 to the 1/2. Then minus 1 to the 1/2, which is just 1. Well, that first term is infinite. So this limit is infinity. The integral diverges. So what we conclude is that this series must also diverge by the integral test. Let's now examine series n equals 1 to infinity of n over n squared plus 1 squared. So we let f of x equal x over x squared plus 1 squared. To determine whether it's decreasing, take a look at f prime. Right, so this is quotient rule. So the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over denominator squared. After simplifying, we should get 1 minus 3x squared all over x squared plus 1 cubed. Now what we want to do is consider one to infinity. So set this equal to 0, first of all. Let's solve it. Right, remember, we want to find critical points, right? So we get 1 minus 3x squared is 0, which implies that x is plus or minus root 1/3, which are both less than 1, right? Which means 1 to infinity this interval is either going to be completely increasing, monotonic increasing, or monotonic decreasing. Pick any value 1 to infinity. And I don't know why I wrote a cubed there. My apologies. No, yes, that is cubed. Sorry. Right? Notice, if we pick, I don't know, 5. Numerator is negative. Denominator, of course, is always going to be positive. We get f of 5 is less than 0. Or f prime of 5, I'm sorry, is less than 0, which means that f itself is decreasing. For x greater than or equal to 1. Now, if we look, when x is positive, it is clear that f of x is positive. And there are no points of discontinuity, right? So f of x is also continuous for x greater than or equal to 1. Now let's take a look at the integral from 1 to infinity of x over x squared plus 1 squared. I don't know why I'm doing square root. Antiderivative. Okay. 1/2 times -1 times x squared plus 1 to the minus 1 and so what we get is, start with x equals 1 first. We're going to get 1/4. Then minus, when x is b, we get 1 over 2 times b plus 1. Right now, as b goes to infinity, that term goes to 0. We're left with 1/4. That converges. So what we can conclude is that this series converges by the integral test. We now look at a new type of series. And it has this form. Series as n goes 1 to infinity, 1 over n to the b, 1 over n to the p, is called a p-series. Now we look at this series. We're going to examine it. We say let f of x be 1 over x to the p. It is clear that for x greater than or equal to 1, f is positive, decreasing, and continuous. Recall that we showed that this integral was equal to 1 over p minus 1 if p was larger than 1, and it diverged if p was less than or equal to 1. So we can now summarize this. In this theorem, the series n equals 1 to infinity, 1 over n to the p converges if and only if p is larger than 1. Let's consider two series. It's called AN and BN. Now suppose that for all n greater than or equal to some value m, larger than 0, we get 0 is less than or equal to a sub n, less than or equal to b sub n. Let's now suppose that the series b sub n converges to S. Then notice that a sub n is bounded above. So we can conclude that this series converges. Let's suppose instead that the series a sub n diverges. Then we must have that b sub n diverges. Otherwise, we would arrive at a contradiction. Specifically, we would contradict what we just said. If b sub n converges, then a sub n converges. We can summarize this below. This is known as the direct comparison test. Assume that there exists some m larger than 0 such that 0 is less than or equal to a sub n, less than or equal to b sub n, for all n greater than or equal to m. If series n goes from 1 to infinity, b sub n converges, then the series n goes from 1 to infinity of a sub n converges. If the series n equals 1 to infinity of a sub n diverges, then the series n equals 1 to infinity of b sub n diverges. Let's examine the series n equals 1 to infinity of 1 over the square root of n times 3 to the n. Now, notice that the term 1 over root n times 3 to the n would be less than or equal to 1 over 3 to the n, right, for all n larger than 1. Now, let's examine the series n equals 1 to infinity, 1 over 3 to the n. Well, we can rewrite that as the series n equals 1 to infinity of 1/3 all to the n. Notice that this is geometric, with r equal to 1/3 and c equal to 1. Which means it converges. Therefore, our original series also converges by the direct comparison test. Let's now examine the series n equals 2 to infinity. 1 over n squared plus 3 to the 1/3 power. Now we want to try and compare this with direct comparison. So we claim that n cubed is greater than or equal to n squared plus 3 for n greater than or equal to 2. What we do is we say, okay, well, let f of x be x cubed minus x squared minus 3. We want to show that for x greater than or equal to 2, f of x would be greater than or equal to 0. To do this, take a look at f prime. What we get is 3x squared minus 2x, which equals x times 3x minus 2. If we set this equal to 0, what we get is x is either 0 or 2/3. So if we just take a look at the interval 2 to infinity, take a look at f prime. Let's pick a value 5, right? We'll get 3 times 15 minus 10. That is clearly going to be positive. So what this is saying is that f of x is increasing for x greater than or equal to 2. Now if we take a look at f of 2, 8 minus 4 minus 3 is 1. Therefore, f of x is increasing and bounded below by 1. This means that f of x will be greater than 0 for all x greater than or equal to 2. This proves that n cubed is greater than or equal to n squared plus 3, which is what we wanted. So we start with that. N cubed greater than or equal to n squared plus 3. This means that 1 over n cubed would be less than or equal to 1 over n squared plus 3. If we now take the cube root of both sides, we get 1 over n is less than or equal to 1 over n squared plus 3 to the 1/3 power. Now take a look at this series. This is a p series with p equal to 1. Specifically, this has a special name. This is known as the harmonic series. So p series where p is 1 is called the harmonic series, or is just called harmonic. Well, this diverges, right? P series converges if and only if p is 1. So we found a smaller series that diverges. So we conclude, and I should have put, sorry, that should have been n equals 2, not n equals 1. So our original series also diverges by the direct comparison test. Let us now suppose that we're given two sequences, AN and BN, which are positive. And we're also going to say let L be the limit of AN over BN. If L is finite and if the series Bn converges, we can choose some number R which is larger than L such that 0 is less than or equal to AN over BN, which is less than or equal to R. Right, and this is for all N sufficiently large Notice what this means. We would get that A sub n is less than or equal to R times B sub n. Since R is a constant, we can write the series R B sub n as R times the series of B sub n, which converges, right? This means that AN converges by the direct comparison test. On the other hand, if L is non-zero, and if A sub n converges, what we do is we define a number, k, to be the limit as n approaches infinity of B sub n over A sub n. Well, clearly k is just the reciprocal of L. So if L is finite, then so is K. If L is infinite, K is 0. By using the argument we just made, we can conclude that the series Bn converges. We now summarize this. And this is the limit comparison test. be positive sequences right? So we have 3 possibilities. L is greater than 0. I should say if L is larger than 0. Then AN converges if and only if BN converges. If L is infinite, and AN converges, then BN converges. Finally, if L is equal to 0 and BN converges, then AN converges. Let's go ahead and examine the series n equals 1 to infinity. I'm sorry, n equals 2 to infinity of n squared over n to the 4th minus n minus 1. Now, for very large n, notice that this term, n squared over n to the 4th minus n minus 1, behaves like n squared over n to the 4th, which is just 1 over n squared. So why don't we take AN to be that term, and then BN to be 1 over n squared. So let's take a look at the limit. Notice this becomes the limit as n approaches infinity of n squared times n squared over n to the 4th minus n minus 1, and that limit is equal to 1. Take a look. That series, 1 over n squared, is a p series with p equal to 2, and so it converges. So, this series converges by the limit comparison test. Now let's look at the series n equals 3 to infinity of 1 over the square root of n squared plus 4. Now again, for sufficiently large n, the term 1 over the square root of n squared plus 4 behaves like 1 over the square root of n squared, or just 1 over n. So we take that to be our Bn. So limit as n approaches infinity of 1 over the square root of n squared plus 4 all over 1 over n is the limit as n approaches infinity of n over the square root of n squared plus 4, which equals 1. So this series is the harmonic series, which diverges. So this series diverges by limit comparison.